All right, welcome to The Explainer. Today we're going to get our hands dirty and look under the hood of what makes a blockchain, well, tick. And let me tell you, it's not some kind of digital magic. It's actually a really clever mix of data structures, all designed to create trust where there often isn't any. So, let's dive right in. So let's kick things off with the big question, the one blockchain was basically invented to solve. Think about it. In our digital world, how do you prove anything? How do you prove a payment was actually sent? Or that a file is the original, without having some big central authority, like a bank or a government, to stamp it and say, yep, this is legit? The answer, and really the core idea here, is something called a distributed ledger. Now, the easiest way to picture this is to think of a magic notebook. But instead of just one person having it, imagine that thousands of people all have an identical, self-updating copy. The moment someone writes something new in their notebook, boom, it magically appears in everyone else's, all perfectly in sync. No central keeper, just a shared, unbreakable record.
Okay, so how do we actually build this thing, this magic, trustworthy notebook? Well, like any good story, it starts small. It all begins with the smallest possible piece, a single entry.
So every single entry in this digital notebook has a name. It's a transaction. And it can be super simple, Something like, Alice sends 5 coins to Bob. That's it. But that simple little record, that's the foundational atom, the basic building block for this entire system. But wait, how does the system even keep track of the money? It's actually pretty fascinating. Unlike your bank account, which just has a balance, a lot of blockchains track individual chunks of value. So when Alice pays Bob, her whole chunk of money gets, well, spent. It's gone. In its place, 2 brand new chunks are created, one for Bob and another one with Alice's change. It's kind of like paying for a coffee with a $10 bill. You don't just subtract the price from the bill, right? No, that specific $10 bill is gone forever, and you get your coffee and some new bills and coins back as change. Same idea here. Okay, but if you just had a constant, never-ending stream of these single transactions, it would be total chaos, right? Just a messy list. So to bring some order to it all, the network grabs a whole bunch of recent transactions and bundles them together. Going back to our notebook idea, it's like we're taking all these little notes and organizing them neatly onto a fresh page. And in the world of blockchain, that page has a special name. It's called a block. And this is where we start to see the big picture come together. Each new page, each new block is sealed to the one that came right before it using some pretty powerful cryptography. What you end up with is this long, chronological, and pretty much unbreakable chain of pages, stretching all the way back to the very first one ever made. And well, there you have it. That's the chain in blockchain. Now let's look closer at one of these pages. Every single block has what's called a header. You can think of it as the page's, its administrative section. It's got the boring but crucial stuff. A unique ID for this specific page, the ID of the previous page, which is what forges that link we just talked about, and a timestamp for when it was created. But it also holds 2 really important security elements that we're about to get into. A special number called a nonce and a summary of all the entries called the Merkle.
So what exactly makes this chain so incredibly secure? How does it become tamper-proof? Well, the secret sauce is something that works just like a digital wax seal from the old days.
In that digital seal, it's called a cryptographic hash. It's basically a special algorithm that could take any amount of data, all the transactions on our page, the whole shebang, and squish it down into a unique string of letters and numbers. It's a digital fingerprint. And the crazy thing is, if you go back and change anything at all on that page, even just one tiny comma, the entire fingerprint changes completely. It's totally unrecognizable.
Okay, and here is the absolute key. This is the secret ingredient. When the network gets ready to add a new page to the notebook, it takes the digital fingerprint of the page before it and bakes it into the data of the new page. So the fingerprint of block 10 is actually part of what makes up the fingerprint of block 11. You see, each new seal is literally built on top of the last one, creating this interconnected chain of digital trust.
And this is what makes the whole history basically tamper-proof. Let's say some hacker tries to go back to an old page and change an entry, maybe to give themselves more money. The second they do that, the fingerprint for that old page changes. But remember, that old fingerprint was used to create the seal on the next page. So now there's a mismatch and that seal breaks. And since that seal is broken, the next one breaks too, and so on and so on. It creates this massive, obvious cascade of broken seals all the way down the chain. The fraud sticks out like a sore thumb for everyone to see. All right, so we've got this super secure chain of pages. Awesome. But here's a new problem. A single page, a single block, can have thousands of transactions packed into it.
So how on earth does the network check all of them without grinding to a complete halt? I mean, just think about it. If every single computer, every node on the network, had to download and recheck thousands of transactions every 10 minutes just to confirm that one of them was valid, the whole system would just collapse. It's just not practical. It's not scalable at all.
So what's the solution? Well, it's this incredibly clever, really elegant data structure called a Merkle tree. And honestly, the best way to think about it is like a super efficient table of contents for the page. Instead of having to read every word on the page to know it's there, the Merkle tree summarizes everything down to one single ultimate fingerprint. And that fingerprint is called the Merkle root.
So how does it work? It's pretty cool, actually. The system starts at the bottom, takes transactions in pairs, and creates a hash of them. Then it takes those resulting hashes, pairs them up, and hashes them again. You see the pattern? It just keeps doing this, pairing and hashing, rolling everything up higher and higher on this tree structure, until at the very top, you're left with just one single hash. That's your top hash, your Merkle root. And that one little hash is the only thing that needs to go into the block's header.
What's amazing about this is the incredible efficiency it creates. Let's say you need to prove your transaction is in that block. You don't need to show anyone the other thousands of transactions. Nope, you just have to provide the handful of hashes that make up your specific branch on the way up the tree. It's an unbelievably fast and lightweight way to prove something's in the block without needing the whole block.
So, okay, we figured out how to build a secure and efficient chain. But is the chain the only way to do this? To structure a distributed ledger? Not at all. Let's switch gears and look at a totally different approach.
What you're looking at here is called a directed acyclic graph, or DAG for short. Now, instead of that neat orderly line of blocks we've been talking about, a DAG looks, well, it looks more like a web or a tangled net. The way it works is really different too. When you want to add your own transaction to the web, you first have to pick a couple of older, unconfirmed ones and verify them. So just by using the network, you're actually helping to secure it. It's a pretty neat system.
And this completely different structure, as you can imagine, leads to some really interesting trade-offs. You can see it in the table here. DAGs are generally way faster, they can handle a lot more traffic, and the fees are usually lower, mainly because you don't have blocks or miners to deal with. But there's always a but, right? Traditional blockchains are often seen as more secure, more robust, because their models for reaching agreement have been battle-tested for years.
Okay, so we've looked at the chain and we've looked at the web. So what's the big takeaway here? What does this all mean for where we're headed?
What this really shows us is that we're in a state of constant evolution. The classic blockchain structure, it gave us something incredible, rock-solid, tamper-proof security. But these newer structures, like DAGs, they're chasing something else. They're all about speed and massive global scale. And what that brings up is this fundamental trade-off, this big question: what's more important, nearly perfect security or lightning-fast speed for everyone? The way we end up answering that question is probably going to define the next chapter of our digital world. Thanks for joining me on this explainer.